The encryption protecting your data has a quiet expiration date. Right now, almost everything you do online is protected by math. When you log into your bank, send a message, or buy something online, your data gets scrambled using a cryptographic system that's incredibly hard to break. Hard for a normal computer, anyway. The problem is that quantum computers don't play by the same rules, and that changes everything about how we think about keeping information safe. Let's start with why today's encryption works so well. Most of the systems we use rely on a simple idea. It's easy to multiply two giant prime numbers together, but if someone gives you the result and asks you to figure out which two primes made it, that's brutally hard. A regular computer would need longer than the age of the universe to brute force that problem at scale, so we built encryption around it. We called it RSA, and it's been the backbone of internet security for decades. Quantum computers approach that problem completely differently. They use something called Shor's algorithm. Without getting too deep into the physics, a quantum computer can explore many possible answers at the same time instead of trying them one by one. For the kind of math that underpins RSA and similar systems, that's a game changer. A powerful enough quantum computer could crack those problems in hours or even minutes. Now here's the part that trips people up. That quantum computer doesn't exist yet, not at the scale you need to break real-world encryption. Today's quantum machines are impressive in the lab, but they're noisy, error-prone, and nowhere near large enough to run Shor's algorithm against modern key sizes. So why are we worried now? Because of something called harvest now, decrypt later. The idea is simple and genuinely unsettling. An attacker could be collecting encrypted data today, stuff they can't read yet, and storing it. Then when a powerful enough quantum computer exists, years from now, they decrypt everything at once. If any of that data is still sensitive by then, it's exposed. So the threat isn't just future. In some ways, it's already in motion. That's why cryptographers and standards bodies started working on solutions well before the hardware catches up. The U.S. National Institute of Standards and Technology, NIST, spent years running a global competition. They invited researchers from around the world to submit new encryption algorithms, ones built on math that even a quantum computer would struggle with. Those new approaches don't rely on prime factoring. They use different mathematical structures. One big category is called lattice-based cryptography. Imagine hiding a secret inside a complex geometric grid with billions of dimensions. Finding the right point in that grid is hard for classical computers, and as best we know, hard for quantum ones too. Another approach uses problems based on error-correcting codes. Another uses hash functions in clever new ways. The details get deep fast, but the core idea is the same. Find math problems that quantum speed doesn't help you solve. NIST finalized its first set of post-quantum cryptography standards in 2024. 3 algorithms made the cut for now. MLKEM for key exchange, MLDSA for digital signatures, and SLHDSA as a backup signature scheme. These aren't theoretical anymore. They're real standards that software and hardware can start implementing today. So what does the transition actually look like? That's where it gets practical and a little complicated. Encryption isn't just in one place. It's baked into operating systems, browsers, VPNs, hardware chips, cloud services, banking infrastructure, medical devices, satellites. Updating all of that takes time, a lot of time. Experts compare it to the shift from older internet protocols, something that took over a decade to fully roll out even when everyone agreed it needed to happen. The good news is that this transition is being treated as an engineering problem, not a crisis. Many organizations are already doing what's called a cryptographic inventory. That means mapping out every place in their systems where encryption is used, figuring out which pieces are most exposed, and prioritizing what to update first. It's the same approach you'd use for any large infrastructure upgrade. One important concept here is crypto agility. That's the idea of building systems so that the underlying encryption algorithm can be swapped out without rebuilding everything from scratch. If your software is crypto agile, you can update the algorithm when a better one comes along without tearing down the whole structure. It's like designing a building with standardized electrical outlets so you can change the power standard later without rewiring every room. There's also a hybrid approach being used in the transition period. Some systems are running classical and post-quantum algorithms side by side. Both have to be broken for the data to be exposed. It's extra overhead, but it gives you protection while the new standards get tested in real-world conditions at scale. The honest reality is that no one knows exactly when a cryptographically relevant quantum computer will exist. Estimates range widely. Some say a decade, some say 2, some say longer. But the math of the migration timeline is pretty clear. If it takes 10 to 15 years to fully update global infrastructure, and the threat could arrive in roughly that same window, then starting now isn't early. It's exactly on time. Post-quantum cryptography isn't about panic. It's about recognizing that the tools we use to protect information need to evolve, and that the evolution takes planning and lead time. The algorithms are ready. The standards are published. The work is underway. The question now is how quickly the rest of the world can follow the map that's already been drawn. For most of us, this will happen quietly in the background, just like every other major infrastructure upgrade. Your browser will get updated, your apps will patch, your bank servers will migrate, and the math protecting your data will keep working, just built on a different foundation, one that's designed to hold up no matter how powerful the computers get.